Hello again. This is section 3.2, polynomial functions and their graphs. So what we're going to look at in this section is how can we look at the equation of a function now and actually determine what it looks like, at least somewhat what it looks like, without even having to use a graphing device. All right, so a polynomial function of degree n is a function of the form p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on until we get down to some a sub 0, which is just a constant term. Okay, now that form looks a little ridiculous, right? But just keep in mind here, the a sub n, the a sub n minus 1, all of those a values are numbers. Okay, so those give us the coefficients of our polynomial. Then x is the variable, and then the n minus 1, and so on. Those are just the exponents along the way, right? So when we actually write this thing out, it's just going to be a number times x to some power plus a number times x to some power, and so on. So even though the form looks a little crazy, right, just keep in mind the a's are just coefficients, they're numbers, the x is the variable, and then all the n's and n minus 1s, those are just the exponents of your x now, okay? Now, those numbers, right, like I said, those are called coefficients, right? So all the a values there are going to give us the coefficients for our polynomial. The a sub 0 is the constant coefficient, okay, meaning it's the constant value because it doesn't have a variable on it. And then the a sub n is what we call the leading coefficient, right? So whatever that coefficient is on your highest exponent term is always what we call the leading coefficient. And then the entire thing, a sub n times x to the n, is what we would call the leading term. Okay, so that entire first piece here, a sub n times x to the n, is the leading term, and then just the coefficient of that would be the leading coefficient. Now, some polynomials here, right? We have 4x minus 7. So if we're talking about the terminology we just used on the last slide, the degree of this polynomial would be 1, because the highest exponent on any of your variables is 1. We have x to the first power. The leading term then is the entire 4x. And then the constant term of this one is just going to be the minus 7, right? Because there is no variable on that term. Notice here they do keep the sign with the number there, right? So instead of just saying 7 as our constant term, it is the negative 7 because there's a minus there. Okay, now the second one, we have x squared plus x. The degree of that one's going to be 2 because our highest exponent on our variable is 2. The leading term is just going to be the x squared in that case. And the constant term here, notice there is no term that doesn't have a variable, so we would say that our constant term is 0 in this case. And then the third one here, we have 2x cubed minus 6x squared plus 10. Again, we look for the degree, which is the highest exponent on one of your variables. In this case, that's a 3, so our degree is 3. That means the leading term is the entire 2x cubed. And then the constant term for this one is the positive 10 there at the end. And then finally, negative 5x to the fourth plus x minus 2. Degree would be 4 because that's our highest exponent. Leading term then is negative 5x to the fourth. And then our constant term, again, we would keep the sign with the number. That's going to give us a negative 2 there. All right, so now we want to sketch graphs of the following functions. Now, I'm going to say because we actually know how to put these things in Desmos or a graphing calculator, rather than actually sketching them, I want to think about these in terms of transformations, right? So thinking back to our transformation knowledge that we have all the way back from Unit 1, I want to think about what we know about each of these functions now. So for the first one, the parent function of negative x cubed is just going to be the x cubed graph, right? And so we've talked about what that graph looks like, but now I just want to think about what the transformation is that's being applied here. So remember, if you put a negative in front of a function, right, outside the parentheses, not grouped with the x in this case, this is going to give us a reflection over the x-axis. Okay, so again, that's what I'm more interested in here is can you recognize the transformations, identify your parent function first, and then think about what type of transformation is being applied to that parent function. Now, if we look at q of x, this time our parent function is actually going to be x to the fourth power. And again, you could definitely graph that in your graphing calculator or in Desmos if you want to. But again, I want to think about this as a transformation now. So we have x minus 2 raised to the fourth power. This time that -2 is grouped with the x inside the parentheses, and so that's going to give us a horizontal shift. And just remember that those are always backwards from what you might expect, right? So that -2 is actually going to shift this to the right 2 units. Right. And then the last one here, our parent function, is actually going to be x to the 5th power. And so now when we look at our transformations, we actually have 3 different things that are going on this time. Okay, so I'm going to start here with the negative. Because I have a negative out front, that's going to give me a reflection over the x-axis. Now I'm looking at the 2, the coefficient in front of the x to the 5th. Well, remember, whenever you multiply by something bigger than 1, that's going to give us a vertical stretch by that factor. We have a vertical stretch by a factor of 2. All right. And then the only other thing we have here is that +4. Notice the +4 is outside, not grouped with the x this time. And so that's going to give us a shift. And because it's outside, it's going to go up 4 units. So again, we could take our parent function, the x to the 5th function, reflect it over the x-axis, stretch it vertically by a factor of 2, shift it up 4 units, and that should give us the graph that we would have. But again, I know you have access to your graphing calculator in Desmos, so you can definitely put these things in there to see what they look like. I'm more interested in, can you recognize what the transformations are based off of the equations themselves? Okay. All right, now in behavior of a polynomial. Okay, so the in behavior of polynomial, and that's just the form that we just looked at a minute ago, is determined by the degree n and the sign of the leading coefficient a sub n. Okay, so there's 4 different scenarios that we could run into. The first one here is if we have an odd degree and our leading coefficient is positive. Okay, so if both of those things are true, then our graph is going to look something like this, right? It's going to go down to the left, it's going to go up to the right, and we don't know exactly what's happening in the middle, which is why we use those dotted lines here, right? Because different polynomials are going to have a different number of terms in them and that kind of thing. Okay, so all we're looking at now is what's happening at the ends, in this case with an odd degree and a positive leading coefficient. It's going to go down to the left, up to the right. Now, the way we actually describe that is we would say that as y approaches negative infinity, x approaches negative infinity also. And so as it goes down and to the left, our y values are going to negative infinity, our x values also going to negative infinity, so that would be the end behavior on the left-hand side there. Now on the other side, now we're going to say as y goes to positive infinity, x is also going to positive infinity, right? So as I go to the right towards positive infinity on the x, I'm also going up towards positive infinity on the y. All right, now the next one here, we're still looking at an odd degree, but now our leading coefficient is a negative value instead. Okay, so when that happens, we actually end up with a reflection over the x-axis, and so now the left-hand side actually goes up and the right-hand side goes down. And so the way we would describe that is we would say y approaches infinity as x approaches negative infinity, right? Because as I'm going to the left on the x-axis, I'm going up on the y-axis. And then the other side of that would be that y approaches negative infinity as x approaches positive infinity. Okay. All right, so that's the 2 cases where we have an odd degree of our polynomial, and then we have a leading coefficient that's either positive or negative. Now, the other cases would be when we have an even degree of our polynomial. So if our highest exponent is an even number instead, the first one here says our leading coefficient is positive. So that's what your graph's going to look like. Again, all we're looking at are the end behaviors here, because the middle of the graph, that dotted piece, could look like anything, right? It could go up and down a certain number of times, depending on what your polynomial actually is. Okay, but the ends in this case will always look like this. It's going to go up and to the left, up and to the right. So we would say that y approaches infinity as x approaches negative infinity, and y also approaches infinity as x approaches positive infinity. Okay, so as I go to the left and as I go to the right, in both cases, the graph is going up. So in both cases, y is approaching positive infinity. Okay, then our last case here, again, we have an even degree. This time our leading coefficient is going to be negative, though. Again, that's going to give us that reflection over the x-axis. So now both ends are going down instead of up. So we would say that y approaches negative infinity as x approaches negative infinity. That's the left-hand side. And y approaches negative infinity as x approaches positive infinity. That would be the right-hand side. But again, both of those are going towards negative infinity on the y, whether I'm going to the left or to the right. Now again, the reason this is useful is because now if we just look at a polynomial and we just look at the leading term, look at the leading coefficient, look at the degree, we can actually determine what the ends of that polynomial are going to look like, right? And eventually we're going to look at how we figure out what the middle part looks like too. But for right now, right, that gives us a lot of good information about what this graph should look like just based off that leading term. All right, so here we want to determine the end behavior of this polynomial. All right, so again, all we have to really look at is this leading term, because that's going to give us all the information we need about the end behavior. So first thing I'm going to look at is my degree. Well, the degree in this case is 4. That's our highest exponent. And what we care about is whether that number is even or odd. Well, 4 is an even value. So what that tells us now, if you think back to the previous slide, whenever you have an even degree, both ends of your polynomial are going to be going in the same direction. They're either both going up or they're both going down. Okay, so now I know my end behavior going in the same direction. The next thing I'm going to look at then is my leading coefficient. Okay. In this case, our leading coefficient is a -2. Now again, what I care about this time is whether that's a positive value or a negative value. Well, in this case, we have a negative leading coefficient. So what that tells us is because our degree is even and we know the ends are going in the same direction, the negative coefficient now tells us that both are going down. Again, the degree tells us, are we going in the same direction or opposite directions? And then the leading coefficient, whether it's positive or negative, is going to give us which direction we're actually going now on each side. Okay? So if you were to kind of sketch this out, what we know then is that both ends of this are going down on the left and the right. And again, we don't really know exactly what's happening in between, right? But we do at least know this much about our graph. Again, the way we would describe that is we would say that y is approaching negative infinity as x approaches negative infinity, and y is approaching negative infinity as x approaches positive infinity. So the first piece tells us what's happening on the left-hand side of that graph, and the other one tells us what's happening on the right-hand side of that graph. All right, so now we want to determine end behavior for this polynomial. We have 3x to the 5th minus 5x cubed plus 2x. All right, so same thing, we're going to look just at that leading term. So we have 3x to the 5th. First thing I'm looking at is my degree. Well, in this case, the degree is 5. And now we care whether that's an odd value or an even value. 5 is odd. And so because we have an odd degree now, what that tells me is that my ends are going in opposite directions. Now, once we have the degree, now we're going to look at the leading coefficient. I'm just going to abbreviate that LC from now on. The leading coefficient this time is 3. Now, this time we care whether that's positive or negative. Well, the leading coefficient this time then is a positive value. And so what that tells us is that the left-hand side is going down and the right-hand side is going up. Okay, and I'll flip back and just show you, in this case, we have an odd degree with a positive leading coefficient, odd degree, positive leading coefficient. That's that first graph we looked at. That's how I know it's going to be going down to the left and going up to the right. Okay, so now if I were to sketch this, and all I know is that this end on the left is going down, this end on the right is going up, and we could have some other stuff going on in between that we don't really know exactly, right? So as long as you understand the end behaviors here, based off of that leading term, that's what we're looking for. Now again, in the homework, you're going to be asked to describe it in terms of as y approaches something, x approaches something. So we would say y approaches negative infinity as x approaches negative infinity, and y approaches positive infinity as x approaches positive infinity. So as I go to the left, I'm going down, and as I go to the right, I'm going up. That's what that says. Okay, now, the next piece of this says to confirm that p and its leading term, q of x equals 3x to the fifth, have the same end behavior by graphing them together. So what I'm going to do, I'm going to switch my graph, I'm going to switch over to Desmos. We're going to look at both of those graphs in Desmos together just to verify that they both have the same end behavior. So our original graph here was 3x to the fifth minus 5x cubed plus 2x, right? And you can see in this case that that end behavior does match what we got, right? It's going down to the left, it's going up to the right. But now, if I were just to graph y equals 3x to the fifth, just the leading term of that, notice here that blue graph also has the same end behavior, right? It doesn't have as many turns in it as the first graph did, okay? But the end behavior, to the left, I'm still going down, to the right, I'm still going up. And so that leading term is all we really need to get what the end behavior is going to be. The other stuff is just going to give us all the extra turns in between now. Okay. All right. Real zeros of a polynomial. Okay, so if p is a polynomial and c is some real number, the following statements are equivalent, meaning if you know one, you know them all. Okay, so number one says c is a zero of p. Number two says x equals c is a solution of the equation p of x equals 0. So if I set my polynomial equal to 0, x equals c is a solution to that equation. The third part says that x minus c has to be a factor of the polynomial p of x. And finally, c is an x-intercept of the graph of p. Again, all of these statements now are equivalent to each other. So if you know one of these things is true, the other three have to be true. That's going to be extremely important as we move forward, because some of our problems are going to give us one of these statements, and we then have to understand how we can apply it to understand the other three have to be true, right? Or sometimes you might be asked to find one of these things, but you can actually use the other ones to find it, right? So understanding they all mean the same thing, all four are equivalent, is going to really help us. Now, intermediate value theorem for polynomials. Okay, so if P is a polynomial function and P of A and P of B have opposite signs, there exists some value C between A and B for which P of C equals 0. Now, it's a lot of words, right? So let's think about what this actually says. I'm going to sketch a graph here. And so what I know is that I have an X value of A and an X value of B. So along my X axis here, I'm going to put my A and my B. Now, we have a polynomial function where P of A and P of B have opposite signs. Well, P of A and P of B are the Y values now of my polynomial. And they have to have opposite signs, meaning one has to be positive, one has to be negative. It doesn't matter which is which, okay, but I'm just going to put P of A up here, and I'm going to put P of B down here, meaning that I would have a point at A, P of A, and I would have another point down here at B, P of B, right? Those are points on my polynomial function. Okay, but they have to have opposite signs according to this theorem now. If that's true, then there's going to be at least one value C between A and B, right? So somewhere in between A and B, there's going to be a C value for which P of C is equal to 0, meaning the Y value at C is equal to 0. And the reason this has to be true is that polynomials are going to be nice, smooth curves. And so if I go from A to B, at some point in between there, I'm going to have to cross through some C value. So basically, that's all this is telling us now. The intermediate value theorem just basically says, if you have an A and B value along your x-axis, P of A and P of B have opposite signs, somewhere between A and B, you're going to have an x-intercept. You're going to cross the x-axis somewhere between those two values. All right, example 4 now. So now we want to sketch the graph of the polynomial function x plus 2 times x minus 1 times x minus 3. Now notice, this is in factored form for us, right? So we have a couple of things we need to think about. The first thing I want to think through is my end behavior, right? Because that was the first thing we talked about in this section. Well, to figure out end behavior, we need to know what the leading coefficient is going to look like. This is in factored form, so we don't really have the leading coefficient. But if you think about it, to get that leading coefficient, all I'm going to do is multiply those three x's together. Because if I were to actually distribute all this out, my leading coefficient, that's going to be my highest exponent, is that x times x times x. Well, because they all have a coefficient of 1, 1 times 1 times 1 is just 1, and then x times x times x, that tells me my leading term now is just x to the third power. Now, because of that, I know that my degree is going to be 3, and I know that my leading coefficient is going to be 1. Now, using that information, we can figure out what the end behavior is going to be. Okay, so we know we're looking first, is the degree even or odd? 3 is an odd value, which means that our ends are going in opposite directions. Now, the leading coefficient, we look at whether that's positive or negative. This time we have a positive leading coefficient. And so that tells us that the left-hand side of our graph then is going to be going down, and the right-hand side is going to be going up. And again, that goes back to that very first graph when we have an odd degree with a positive leading coefficient, our end behavior is going to be down and to the left, up and to the right. All right, now the other thing we can look at now are the zeros of our polynomial. Because if you remember, we have those 4 statements that are all equivalent. If C is a 0, then x equals C is a solution, which means x minus C is a factor, and C has to be an x-intercept of our graph then, right? So if I can find the zeros from the factors, then I have my x-intercepts, right? That's what that tells us. So I know the factors of this polynomial already. So all I have to do now is set each one of those factors equal to 0. So x plus 2 equals 0, x minus 1 equals 0, and x minus 3 equals 0. Now, solving each of those, we're going to get x equals negative 2, x equals positive 1, and x equals positive 3. These are the zeros of our polynomial, but we know that they're also now the x-intercepts as well. So because we have the factors, if we set the factors equal to 0 and solve, that's going to give us the zeros of that polynomial, but those zeros are also the x-intercepts of the graph of that polynomial now. So now we actually have a lot of information to help us sketch this graph. So if I sketch this out, first thing I'm going to do is I'm going to put my x-intercepts, my zeros, along my x-axis. And so I know I have one at negative 2. I'm going to have an x-intercept over here at negative 2. I'm going to have one at positive 1. And I'm also going to have one at 3. And so those are my x-intercepts. The other thing I know is my end behavior. I know that to the left, I'm going to be going down, and to the right, I'm going to be going up. So I know this piece of my graph is going to go down this way, and over here, it's going to be going up like this. Now it's a matter of filling in the middle. Now, we still don't quite have everything we need to get a perfect graph, right? But I at least know that I need to cross through the x-axis at all of these points. So I know I'm going to need to go up like this and pass through this point, which means I'm then going to have to turn and come back down to go through this point. And then I'm going to have to turn and go back up to go through that point so that I can connect my end behaviors correctly now. So by knowing the zeros, knowing the end behavior, I can get a pretty decent sketch of what that graph's going to be. Now, again, I don't know the highest and lowest points, those turning points yet, right? We will look at that. Okay, but for right now, that's just a sketch of what this graph might look like. And again, you have access to a graphing calculator in Desmos, so you can always feel free to put these things in there, right, just to kind of check yourself and see how accurate you were. All right, now, this time we're going to let p of x equal x cubed minus 2x squared minus 3x. First thing we want to do is find the zeros, and then we're going to try to sketch the graph based off of that. Now, this time they don't give us the factored form, but the first step is going to be factor, right? So we need to actually factor this thing out. So if I look at this one, first thing I notice is I have a common factor of x. So I'm going to go ahead and factor out my common factor. If I do that, we're going to be left with x squared minus 2x minus 3. Now I'm going to look at what's left in the parentheses there. I have a quadratic trinomial, so I'm going to see if I can factor that into two binomials. Now to get x squared, I'm going to need an x and an x. Only factors of 3 here are 3 and 1. And I know to get a negative 3, my signs need to be opposite, one positive, one negative. And since I want a negative 2x in the middle, I'm going to make the larger value the negative, and the smaller value the positive. So then when I combine those, that will be a negative 3x and a positive 1x. That would actually give us a negative 2x as our middle term there. Now that we have the factored form, we're going to do it the same way we did the last one. We're going to set each one of those factors equal to 0. We'll have x equals 0, x minus 3 equals 0, and x plus 1 equals 0. Now our x equals 0 is already solved, nothing to do there. The next one we can add the 3, so we'll get x equals positive 3. And finally, x equals negative 1. So that answers the first question. That's finding all the zeros of that polynomial now. So if it's already in factored form, look for ways to factor, set each factor equal to 0, and that gives us our zeros. All right, now we want to try to sketch the graph. So the other thing I need now, beyond just the zeros, I need to know what the end behavior is going to look like. So again, I'm going to go back to my leading term here. We know the degree of this one is going to be 3, which means we have an odd degree, which means opposite directions for our end behavior. Leading coefficient this time is 1, which is positive, which means down to the left and up to the right. All right, so now that we have our zeros and we have our end behavior, now we can sketch this. So I'm plotting my points -1, 0, and +3. And again, our end behavior is very similar to the last one because we have that positive leading coefficient and odd exponent. So it's going to look something like this. And now again, we just need to connect these and make sure we actually pass through the x-axis at our x-intercepts. It's going to go up like this, curve back down through 0, and then come back up like this. And again, for right now, I don't know what the highest and lowest turning points are going to be, right? So all I'm really looking for is my end behavior correct? And do we cross the x-axis at the right places, right? That's a rough sketch of what the graph would look like. All right, so now we have p of x equals -2x to the 4th minus x cubed plus 3x squared. Again, first step, we want to find the zeros. So we need to factor just like we did on the previous one. This time, I have a common factor of x squared. So I'm going to go ahead and bring out the x squared. If I do that, that's going to leave us with a -2x squared, a minus x, and a plus 3. Now we look at what's left in the parentheses, see if we can factor that further. Keep your x squared. I know to get a -2x squared, I'm going to need a -2x and a positive x, or possibly a positive 2x and a negative x, right? We'll figure out which way it needs to go. Then I need my 3. The only factors there are 3 and 1. And because I know I'm trying to get a -1x here in the middle, I'm going to put the 3 here and the 1 here, because otherwise, if I put the 3 on the other side, I'm going to end up with a -6x. That's just going to be way too much. So now we just have to look at our signs and see if this is going to work out for us. So if I do negative and negative, then that would give us a -3x in the middle. It would give us a positive 2x here at the end, and that would give us the negative x that we want in the middle. Okay, so that looks like it works out. And again, if you had started with 2x and -x, right, and you couldn't get that to work, right, trial and error, just go back and switch some signs around. In this case, those factors should work. All right, now that we have our factors, now we're just going to set each one of those factors equal to 0. So we'll start with x squared equals 0. Then we have -2x minus 3 equals 0. And finally, x minus 1 equals 0. And now to solve the first one, we need to take the square root of both sides. So when we take the square root, we'd have x equals, technically it's a plus or minus, but plus or minus 0 in either case is just 0. Now the next one, I'm going to add my 3 first. So I have -2x equals +3. divide by the -2. That's going to give us x equals -3/2. And the last one here, we're going to add the 1, so we'll have x equals +1. So that takes care of the zeros of that polynomial. So now the next thing I want to look at is my end behavior, so we can sketch this graph. So again, I'm looking at my degree first. Degree this time is 4. 4 is an even value, which means my ends are going to be going in the same direction. Then I look at my leading coefficient. This time that's a -2. That's a negative value. And that means that both ends, because they're going in the same direction, are going to be going down. All right, so now I have my zeros, I have my end behavior. So now we can sketch this. So I'm going to go ahead and put my zeros on there. I know there's going to be 1 at 0, 1 at -3/2, which is like -1.5, so halfway between -1 and -2. And the other one's going to be over here at +1. And now we look at our end behavior. We know both ends are going to be going down. I'm going to have one end going down like this, and the other end going down like that. Now, we're going to connect these, right? Make sure you go through your points along the x-axis, okay? Now, something interesting is going to happen this time. So I'm going to go up like this. I'm going to come down like this. If I go back up like this, I'm not connected. So we've got to figure out what's happening here, right? So we got to figure out why is it that I have x-intercepts, right? Those 3 x-intercepts. And yet my end behaviors need to be going in the same direction, both going down. So I need to be able to connect this somehow, but I don't have any other x-intercepts, right? Those are the only ones I have to work with. Well, what actually happens this time is this x² right here tells us that this is what we call a double root. Okay, so when we take that square root and we get x equals 0, that x equals 0 is what we call a double root. Because of that, when we actually connect these now, when I go up through this first point and I come down to this point, instead of actually going through the x-axis now, my graph is actually just going to bounce off of that point instead. Okay. And so then once it bounces there, it still needs to go down through this other point, and then I can connect up with my other end behavior. And again, I don't know exactly how high it's going to go on either side there in terms of those turning points. Okay, but just notice here, because we have a double root, because of that x² this time, the graph actually bounces off the x-axis at that point instead of passing through. And that's how we actually keep the end behavior that we need and actually still do touch all of our x-intercepts. Right, so while I'm talking about that, I'm going to go ahead and talk about what I just said. Okay, so this is kind of the generalization of that rule that we just looked at. So if C is a 0 of multiplicity M, okay, this just basically means how many times it happens. Okay. When you see that word multiplicity, that's just saying that 0 happens that many times. Then the shape of the graph of that polynomial at C is going to be as follows. If we have an odd multiplicity, so if our 0 happens an odd number of times, then our graph is going to actually go through the x-axis at that point. Now notice here, they're telling us that M is greater than 1, right? Because with a multiplicity of 1, we already know it's just going to go straight through, right? Like that's not going to change. But in this case, if we have an odd multiplicity, like a 3rd power or a 5th power or something like that, so our 0 happens 3 times or 5 times, it's still going to pass through, but notice how these graphs flatten out a little more, right? So it's not just a straight pass through this time, right? This time it actually levels out at the C value, but then it continues in the same direction. However, if m is even, right, so if it happens 2 times or 4 times or 6 times, again, with m being greater than 1, then it's going to bounce. Okay, and so that's that case that we just looked at where 0 happened 2 times. That's an even number of times. And so our graph had to bounce at that c value at 0. And then notice it could bounce from the bottom also, right? So if you're coming in from that direction instead, and it has an even multiplicity, happens an even number of times, then it's going to bounce the other direction instead. All right, so let's take a look now. Example 8. We want to graph this polynomial function. Okay, so same thing. We're looking for the zeros, thinking about in behavior, and then we're going to use that to actually sketch what this graph would look like. Well, it's already in factored form for us. So the first thing I'm going to do is set each one of those factors equal to 0, find the zeros of this polynomial. So x to the 4th equals 0, x minus 2 cubed equals 0, and x plus 1 squared equals 0. So for the first one here, to get x by itself, I would just take the 4th root. But when I do that, the 4th root of 0 is just going to give me 0. However, just like the other one that we did where we had an x squared equals 0, we would have to say that this has a multiplicity now of 4. So because we started with x to the 4th power, that tells us that that 0 has a multiplicity of 4. Okay, now the next one, my first step to get x by itself, I'm going to have to take the cube root. Again, the cube root of 0 is just 0, so we're left with x minus 2 equals 0. Add your 2, x equals 2. But again, we need to talk about the multiplicity here. Because it was x minus 2 to the 3rd power, that means our multiplicity this time is 3. So whatever that exponent is on your factor, that tells you what its multiplicity is going to be. And then finally, we have the x plus 1 squared. We're going to take the square root. Sorry, I don't really need the 2's there. Okay, so the square root of both sides, that's going to give us x plus 1 equals 0. Subtract your 1, you get x equals negative 1. And in this case, that would have a multiplicity of 2 because 2 was the exponent that we started with. Now, based off of those multiplicities, now that tells us whether we're passing through the point or whether we're bouncing off the point, right? And so when we actually get to sketch the graph, then we'll talk about what's going to happen at each of those points. Now, the last piece we need is our leading term, right? Because if I know the leading term, then I know my in behavior, and then we can sketch this. Well, notice here, none of the x's have coefficients, right? So we know the coefficient of our leading term is just going to be 1 because all those 1's multiplied together is 1. But now the exponent, we have an x to the 4th, we have an x cubed, and we have an x squared. So remember, when we multiply, we actually add exponents. So I know when I add all these x's to, or multiply all these x's together, if I add all those exponents up, my leading term is actually going to be x to the 9th power. Again, that's just from adding the 4, the 3, and the 2 here, right? Because the x minus 2 cubed would give us an x cubed. The x plus 1 squared would give us an x squared. X to the 4th times x cubed times x squared. Add the exponents, we get x to the 9th. Now I look at each of the pieces of that, right? So the degree this time is 9, which is odd, which means opposite directions. Leading coefficient is 1, which is positive. And so that tells us down to the left, up to the right. All right, so now we just need to sketch what we've got here. Again, I'm going to start by plotting my x-intercepts. So we have one at 0, we have one at positive 2, and we have one at negative 1. In behavior, I'm going down and to the left. That's this way. I'm going up and to the right. So that's like this. And so now when we sketch this, we just have to remember, are we bouncing or are we passing through? Okay, so the first one I'm going to get to, if I come in from the left-hand side here, is that negative 1. Okay, so if I look at my negative 1, I know it has a multiplicity of 2, which is an even multiplicity. That tells me that this one is going to bounce because it's even. Okay, so when I get to negative 1 here, I need to make sure that I'm bouncing back down. Now the next 0 I'm going to get to is 0. It has a multiplicity of 4. That's an even multiplicity, which means it's also going to bounce at 0, right? So it has to come back up, but then it's going to bounce again. And again, I don't know how high or low these turning points are, right? So I'm just kind of, randomly putting them somewhere. As long as you got the end behavior and whether it's bouncing or passing through at each of these points, that's the main thing. Okay, so then our last one that we're going to hit is the positive 2. Positive 2 has a multiplicity of 3, which is odd. So I know that this one is actually going to pass through that point. Now, because it's greater than 1, though, right? The multiplicity is 3. It's an odd value. It passes through. But we need to make sure that it kind of levels out at that point rather than going straight through at that point. So it's going to come up like this. It's going to kind of level out. And then it's going to continue up and connect to our end behavior. And so that would be a rough sketch of what this graph would look like now. Again, the things that we know based off of the leading term, we know the end behavior. Based off of the zeros and whether their multiplicity is even or odd, we know whether it bounces off the x-axis at those points or whether it passes through the x-axis at those points. All right, now local extrema of polynomials, right? So when we say extrema, that just means maximums and minimums. So if we have a polynomial function of degree n, the graph of p has at most n minus 1 local extrema. Now, what that means is if our polynomial was like x to the 5th plus 4x cubed minus 2x plus 6, right? All we're looking at now is what is the degree. In this case, the degree of this one is 5. So then we would take the 5, we would subtract 1. So n minus 1 in this case is 4. That tells us that we're going to have at most 4 local extrema. Okay, so at most 4 mins and maxes of that graph now. Now, that doesn't mean we have to have that many, right? We might not. Okay, but we at least know that's the maximum number of mins and maxes that we could have on that graph now. All right, so now all I want to focus on here are the maximum number of local extrema. Okay, that's it. So if we look here at P1 of x, we have x to the 4th plus x cubed minus 16x squared minus 4x plus 48. If I want to know the maximum number of local extrema, all I have to look at is the degree. The degree this time is 4. And remember, the maximum number, the most local extrema you could have, is 1 less than that value. So at most, I'm going to have 3 local extrema. Right, for the next one now, our degree is 5. We would take 1 less than that. So at most, I could have 4 local extrema. Again, we're not saying there are 4. We're just saying that's the most that you could have. And then finally down here, x to the 4th again, That tells us at most 3 local extrema. And again, you can always sketch these in Desmos or in your graphing calculator to see what the actual graphs look like, and then kind of check to make sure that you don't have any more than what you said. I will tell you that the first one here should actually have 3 local extrema. The last one, though, even though it has at most 3 local extrema, because of the form, it's actually not going to have that many. Okay? So it's actually, I think, only going to have 1 in this case. All right, and that's all we've got here for section 3.2. As always, send me those questions in WebAssign as you have them. Come see me during student hours if you need to. Otherwise, have a great day, and I will see you next time.